Good afternoon and welcome to the extra lecture on cryptography network security. So I handed out the slides. They will also be available in Toledo, and I hope to also finish the course this week. So the course version of last year is on Toledo, but the slides always have small updates, as you will see. And hopefully VTK can then produce it in the next weeks, because next week there is no lecture, because I'm away, and the week after there is holidays on 2nd of November, so next lecture. So we have one lecture this week, but then the next one is only November 9. And that should be enough time to produce the course, I hope. In that week, there is also an exercise session, symmetric cryptography. And there is 3 sessions planned. And so you're supposed to attend one of them. So I think one on Tuesday, one on Monday, one on Tuesday, and I think one later in the week. So that's the update on that front. So today we'll talk about public key encryption. Let's make sure I have the right version of the slides. This is the new edition here. Yes. So the concept was already introduced in the second lecture. So now we're going to a bit more in detail on this. There is also some math background for those of you who took applied and discrete algebra in second year. You will recognize a lot of things. For the others, you will find in the course text, you will find a small chapter of 20 pages that gives you the necessary math background to go more in detail for this part. So I strongly recommend that you look at this. You don't need it for this lecture in particular, but you will need it to prepare for the lecture on public key cryptography, exercise session, sorry, on public key cryptography. That will happen somewhere in November. But now I think this lecture you should be able to understand most of it without doing this extra background, because we don't go too deep in the mathematics, only in a few places. So we'll explain more in detail RSA and El-Gamal. RSA already explained to you very quickly. I will now go more in detail. Then again, we'll revisit the Diffie-Hellman key agreement. We also explain El-Gamal encryption. I will also say something more about post-quantum cryptography, a topic I already touched in the second lecture, but we'll go slightly more in detail and so look at how public key cryptography is being used. So for the math background, you can find slides and an article in the course text on Toledo. For most of the things today, you don't need it, but if you want to understand things more in depth, it's good that you study this and that you master this. So we look at the concept of one-way functions and trapdoor one-way functions, and then for one-way functions we explain Diffie-Hellman, trapdoor, RSA, and then I will explain you how to derive El-Gamal from Diffie-Hellman, and then we'll say a few things about post-quantum security. So again, remember that Diffie and Hellman asked themselves in 1975 2 questions. How can 2 people who never have met and only have a public channel, can they still agree on a secret key and can have a private conversation? So this is very important for open networks. For those of you who still want slides, there is still copies in the front here, and they will be on Toledo tonight, but if you want them now, you can pick up a copy here in the front. And so it turns out there is an answer to this problem, and we use it now every day if you use services on the internet, because you never meet in person or you don't have a secure channel with any of the players on the internet, yet you have secure communications with them that cannot be eavesdropped. And second, can you digitally sign documents? We also discussed this concept already. It's important for code updates, but also for signing documents and contracts is increasingly being used. And as we'll see in the next lecture, also for logging in securely. Like if you get access to your healthcare data or to tax on web, You may not have the fun yet to file your taxes, but some of us do file taxes. And then you can actually use public key cryptography to log in as well. So again, symmetric cryptography reduces security, information security of keys. And so how do you deploy those at a large scale? This is cumbersome and expensive. The biggest systems are the GSM system, where there is 5-6 billion users, and you all share a key with the operator in your SIM card. And at this moment, most of us still use a physical SIM card. They get smaller and smaller and smaller. At first was the SIM card, and was the micro SIM, or the micro SIM, the micro SIM, then there was nano SIM. They get smaller and smaller, but in fact what is in there is more or less is a secret key that you share with your operator. And this is used to find out who you are and to encrypt communications, as we will see. But of course that means the operator has a database with all the keys. So it's, even in Belgium where the operators are small, this means the largest operators have a database with 4 or 5 million secret keys. And every time you switch on your phone, they have to consult this. So this is kind of tricky. If this is ever getting hacked, everybody has to get a new SIM card, which will be very challenging. So you see this now that there is a switch to eSIM, so they want to make it actually, what they want to do is they want to more or less use the hardware built in the phone. So modern phones have also secure cryptographic module, and they want to write the key in there, which is easier than having a special cryptographic module with a special key that would kind of come together with the phone. And so the question is, do we need this? And I guess the answer is no. You know the answer because we looked already at Diffie-Hellman. So in public key encryption, just to remind you, you encrypt with, I went one too far. You encrypt with the public key, so the public key is made public, and you decrypt with the private key. So anybody can encrypt, which means you don't know who sent the message to you. So if you go to my homepage, you find my PGP email key, so you can send me a secure email. I'm the only one with the private key who can decipher this message with my private key, but I don't know who sent the message, because anybody can go to my webpage, take an email tool, an encryption tool, and send an encrypted email to me. So it creates a secure channel, but I don't know who sent the message. And of course, we don't solve the problem. We shift the problem to authenticity of public keys. How do you really know it's my public key? And maybe you trust my homepage. It's a secure connection. We'll come back to how secure that is. But more or less, you shift the problem of secrecy of data to authenticity of public keys. So you have to be really sure that the message, or the key belongs in this case to Bob, that only Bob knows the private key. And so a common attack, so for example, if you have a secret conversation, say at your work with Facebook or Meta or whatever your favorite social media, a common attack, this is actually your employer. In Europe it's illegal, but I guess in some settings it happens still. Your employer actually gives your device a fake public key of Facebook. And so you encrypt all your data with another public key where the private key is known to your employer. And so what they do is they decrypt at the gateway of the company, they decrypt all your messages for Facebook in and out. They look at it, and then they re-encrypt it for Facebook, but you don't see this, but it's called the person in the middle attack. And so this can be done by making your device believe that a public key which belongs to your employer actually belongs to Facebook. By the way, in some regulated sectors this is allowed. So, for example, if you look at the banking sector or trading sector, so in the finance sector, employees are monitored because there is a very big risk of insider trading, people who know stuff. There is a risk, as was discovered, of agreements between traders. And of course, that can generate billions of value or lose billions of value. So for this reason, if you work in certain environments, you're monitored, and if you would use Facebook, either Facebook is blocked or they would interrupt the traffic so they can see that you're not giving your insider information through Facebook. So just to show you that public key is great, but there is an assumption that the public key is correct. If the public key is not correct, then it offers you nothing. And in practice, it's not as easy as it sounds. We'll have a whole lecture devoted to how to actually make sure public keys are correct. So we can also do the opposite, do signing stuff. So then we transform with the private key, and we verify with the public key. And this way, Alice can prove that she is the source of information, is linked to her public key. Anybody with the public key of Alice can check that it comes from her. As we mentioned, this is what's being done for code updates, or if you sign documents digitally. But that's the topic of the lecture of Thursday. But so in public key setting, you have clearly separation, just like in symmetric key, you have encryption algorithms, and we saw MAC and hash. In public key setting, you have public key encryption that only gives you confidentiality, but you don't know where the data come from. And you have signatures that give you data authentication. You know who produced the data has not been modified. But you don't have secrecy or confidentiality. So if you want both, you have to do two operations. So the first step for public key encryption is a one-way function. So the idea is you put your data in some function. It's easy to compute this function, but given an output in the range of the function, it's very hard to find an input with that output. So you conceive functions which are easy to compute but hard to invert. And the question is, do such functions exist? And the answer is, we don't know. We can't prove that such functions exist. So we can prove that there is functions that are twice as hard to invert as to compute. But that will not bring you very far with cryptography. If you can prove that the opponent has to do twice as much work as you, that's not very secure. If breaking a system costs only twice as much as encrypting, it's not a secure system. But we do have candidate functions for which we believe that they are one way. So we're actually, we can define them, and we believe that we can see it's easy to compute them, but once we get the result, nobody knows how to go backwards and find the inputs. And if you ask a theoretical computer scientist, he will say, well, take just any random function. You take logical gates, AND and OR gates. You take a 1,000-bit input, you put a few million AND and OR gates and XOR gates, and you put random wires in between them. You can compute this easily, but going back may be very hard. Because in general, actually, Boolean algebra is very hard to solve. That's not a proof, but in general, this is probably true. But of course, as engineers will say, yeah, that's fantastic, but I don't want 1,000,000 gates. I want to build something like this with 1,000 gates or 10,000 gates. Right? I mean, it's not very practical to need 1,000,000 random gates and random wires. If you have to compute it in software, it's a nightmare. Right? 1,000,000 gates, bit by bit. You have to write all your inputs in bits and then do millions of operations. It will be a slow function, it will be a pain. So that's not a good solution. So as we will see in symmetric cryptography, what we do for one-way functions is we build a structured function which we repeat, which is kind of simple but structured, like AES, and then you repeat it many, many times. And AES is a one-way function. If I look at it, so AES has a plain text. It's encrypted to a ciphertext under control of a key. Okay, and so assume I give you the plain text. I take it all zeros. Okay. Then AES is a one-way function from the key to the ciphertext. Because even if I know the plain text, which is all zeros, and I know the ciphertext, there is no one who can find the key except by trying all possible keys. So in that sense, AES is a one-way function. If it was not a one-way function, then you could just take a plain text and a ciphertext and compute a key from that. And AES was broken. But if you write down the equations, you'll find out that they're very complex nonlinear equations, and for now, nobody knows how to solve them. Can we prove you can't solve them? No. We just don't know how to do this, and we believe the problem is hard. So, of course, also if you take a hash function, it's the same thing I already mentioned, like SHA-2 and SHA-3. This is the same thing. You take an input, lots of functions, but they're typically structured and repeated. You give an output. There is no key here, but they're designed in such a way that you can't invert it. Of course, you can try all possibilities, but if that is too much to the 128, you can't do it anyway. Right? That's the idea. Now, in public key, we want to have more structure, and we already have an example of such functions. I take two prime numbers, P and Q. You can generate quite easily primes of 2,000 bits. You can multiply them with a simple program, and now you have the product, and nobody knows how to find the factors. So that's also a one-way function we use in cryptography. Can we prove factoring is hard? No. Nobody can prove that. But it's just that nobody knows how to factor. Okay, so we can't prove there is one-way functions, but we have quite some camelled one-way functions which we use. So I already mentioned this one. So it's not so hard to find two large primes. And if you read the extra material, this is called supervised self-study. Maybe you're probably too young, but I think I mentioned this already in the first lecture. So in the 90s, we had a very wise rector who decided that professors talk too much, which is true, professors talk too much. And so he decided that there should not be 14 lectures, but only 10 lectures. And he said the students are very smart, the remaining material they can learn in self-study. And so this is part of the self-study, is learn the mathematics of number theory, a little bit of number theory, and one of the things is how do I generate large primes? So I need a prime number of 2,000 bits, how do I do that? So you can do this, but then of course, again here I took slightly bigger primes, and my example I showed a bit earlier. So here I took primes of 4 digits, and you multiply them, and I mean I have a program that can do it, and as we saw, you can find on the internet programs that can factor something like 100 digits or so, but by hand would already be a very annoying task to do. If I would say you have to factor this by hand, it's probably hard. So the other thing we saw Diffie-Hellman, another candidate for a one-way function is modular exponentiation. I will show some numerical examples a bit later. But so you take a basis, and that sounds very complex, but in practice, basis is 2. Okay? We don't make our life easy or difficult. If it can be easy, we choose a basis 2. You take 2 to the x is y, exponentiation. That would not be one way, because if you take 2 to the x equal to y, then you take your calculator and you take a logarithm base 2, and then you have the answer. Now, of course, if the number has 100 digits, good luck, your calculator will not work. If you first can't enter the number, because calculators only have 9 or 10 or 12 digits. So you will need a library, but these libraries, they can actually compute this. And by the way, if you studied numerical mathematics, what is used is Newton-Raphson. So they actually iterate until they find a solution. It's not difficult. Okay? But if I add mod n after this, and if n is large, and x is large, then actually we believe it's a hard problem. So if I take the remainder by division of n, this is mod n, then suddenly finding x for a given y is hard, and we call this discrete logarithm. Why discrete? Because there is also continuous logarithm, where the one which you learn in the analysis class, which is just a function which you can invert easily. But discrete logarithm, this is really a very bizarre and random function, and we can't solve this. So the problem is, given a, n, and y, find x such that a to the x mod n is y. And so again, if a is 2, but if n is something like 2, 3, 4,000 bits long, so divided by 3 to get the digits, so 600 to 1,200 digits, it becomes very hard. Nobody knows how to do this. So here's a numerical example. I calculate mod 21. Of course, then it's easy. So 5 to the 4, mod 21 is 16. You can compute this. It's not so difficult. We'll show you also how to do this efficiently if you haven't seen that. So 4 is a solution. So the discrete log of 16 mod 21 with base 5 is 4. But if I would have said base is 5, my n is 21, y is 16, find an x. Well, the best thing you can do is try x0. No, then you get 5 to the 0 is 1. X squared, so x is 2, 5 squared is 25, mod 21 is 4. 5 to the third, you can try possibilities. There is only 20 possibilities, right? Because as we will see, it's even less, but there's actually only 12 possibilities in this case. But you can try all possibilities, and you will find the solution easily. But that's, of course, that works if I have a toy example. But if I have an example of 1,000 bits or 2,000 bits, there is no way you can try all possibilities. Because if you remember, what you can try is something like 2 to the 60, 2 to the 80, 2 to the 90 maybe, but more than 2 to the 100 you can't do. So that doesn't work. So there is no efficient algorithm to do this. There is better algorithms than just trying all possibilities, but even those, as we will see, they break down, they have a certain complexity. Now, one-way functions don't seem so useful, because if I want to encrypt x and I apply a one-way function, I get f of x, I can't go back, so nobody can decrypt. So while cryptography, we show that you need one-way functions, so without one-way functions you can't build cryptography, but if it's only one-way functions, it's not so useful, because you can encrypt, but you can't decrypt. So you want somehow to be able to inverse the function. And so, but we'll show that if you have an extra property, which we call commutativity, then you can actually use one-way functions to agree on a key. So we have Alice and Bob. They've never met and they share no secrets, but they agree on a one-way function that's also commutative, which means the order of operation does not matter. So this is my function f. So what the alpha is the base in our example, so this is a parameter of the function. X is my secret input by Alice, so Alice chooses a secret x, computes f x alpha, and sends it to Bob. Bob does the same thing, generates a secret input y, computes fy alpha, and sends it to Alice. And then what Bob does, it also replaces alpha by fx alpha, the value he got from Alice, and computes fy fx of alpha. And Alice does a similar thing. She takes what she got from Bob and puts it in the place of alpha, so she computes f of x of fy alpha. And if the function is commutative, then the order doesn't matter, and so these two things are equal. And this is a secret key. So that's the general concept. What you need is a one-way function with an extra property, which we call commutativity, which means that if you first apply x and then y in the function, or first y and then x, you get the same result. And so this is the core what you need for key agreement. And so we already saw a concrete example. So one example of such a one-way function is f of x is alpha to the x mod p. So my second input is the alpha, is the base. And as I said, it's 2. And then the prime number p, you also agree. So you can go to the internet, you can use an IETF standard, and say we use SSH or TLS, and then the prime number will be fixed. You have prime number 1 of 2,000 bits, prime number 2 of 3,000 bits, prime number 4 of 4,000 bits. That's it. Also in the banking world, if they use this, they have standards, and they just use standard primes. So it's not that these are secret, they're just commonly agreed because they need certain properties, but everybody checked that these ones are good, and they're being used. So alpha and p are public, so alpha is 2 and p is a public thing. But even then, you can take an x and compute after the x mod p, and nobody knows how to find x. So Bob does the same thing, takes a y, computes after the y mod p, and then sends this to Alice. Then Bob takes f of alpha x and uses as his alpha, so he takes actually what he got from Alice and raised to the power y mod p. And similarly, Alice takes what she got from Bob, alpha to the y, and raised to the power x mod p. So it's what I showed on the previous slide was more conceptual. Here you see a concrete example of such a function, which is modular exponentiation. So now Alice and Bob share a common key, k. And so the question is, if you're eavesdropping the line, can you find the key k? So can you find from alpha to the x mod p and alpha to the y mod p, can you find the key k? And that's known as the computational Diffie-Hellman problem, which means breaking Diffie-Hellman or finding the Diffie-Hellman key. And so we know that if you can compute discrete log, you can definitely break Diffie-Hellman. If I can compute x from alpha to the x mod p, so if I can invert this function, then I can do the same calculation as Alice and I can find the key. If I can compute y from alpha to the y, then I can actually compute like Bob, and I can find the key. But so, if discrete log is easy, Diffie-Hellman is not secure. But we believe discrete log is hard. Can we then show that Diffie-Hellman is secure? You can't find the key? No. This is called the Diffie-Hellman assumption, which says that you can't find alpha to the xy from alpha to the x and alpha to the y. And so in mathematics, if you can't solve a problem, you make an assumption, and this is known as the computational Diffie-Hellman assumption, which says Diffie-Hellman is secure because we believe the computational Diffie-Hellman assumption, which says that Diffie-Hellman is secure. So it's not very satisfying. I'm a bit too critical because, in fact, there was some brilliant work being done in the 90s, and some researchers showed that for some prime numbers, we can show that indeed, if you can't solve discrete log, that computational Diffie-Hellman is the same as discrete log. So if you can actually break Diffie-Hellman, you can also solve discrete log. So the problems were shown to be equivalent for some prime numbers, but not for all. This problem is still open since almost 50 years to prove that this problem holds for all primes. Okay. But of course, if discrete log is insecure, then Diffie-Hellman is insecure. But in general, most people believe these two problems are more or less equivalent. And for some primes, we can show that they're equivalent. So for those of you who find this too abstract, you'll dive into mathematics later when the motivation, this lecture hopes to give the motivation. But so you really have to try these things. Also at the exam, you may have to do this on concrete examples, so you really have to get a feel of how this kind of arithmetic works. It's not very difficult. So I choose a very small prime here, 37, and I choose alpha 2. I promise you, always be 2. It can also be 5, but it's always a small number for... So now if I choose x equal to 10, then alpha to the x, well, that's 2 to the 10, that's 1024. Mod 37, this you can still do with a calculator or with a simple division, and you'll find 25. Okay. Same thing for y. After the y is 2 to the 13, that's 8096. You can compute mod 37 and you'll find 50. So this is, of course, because it's a toy example, you can still do this very easily. But if computing the key is already more challenging, so if I now have to take what Alice does, which is alpha to the y, which is 15 to the power x, which is 10, if you type 15 to the 10 in your calculator, you will get an overflow. Right? And this is, you already get an overflow if you work with 2 digits. You can imagine what happens if you work with 600 digits. You get a big problem. Now there is a very clever trick called square and multiply. What you do is you write your exponent 10 in binary, so 10 is 8 plus 2, okay? And you first compute 15 mod 37 is 15, then 15 square mod 37, this is 225, okay? So my number is now at most 37 squared, so it's still quite small, it's less than 1600. So in this case it's 225, 225 mod 37 I can compute quite easily, it's 3. So now I found x squared, or 15 squared mod 37. How do I find 15 to the 4th mod 37? I just square this again. So 3 is x squared mod 37. So 9 is x to the 4 mod 37. And 81 is x to the 8 mod 37. 81 mod 37 is 7. So you see, in fact, that I do reduce all the time, and the biggest number I ever have to work with is 37 squared. And here I was lucky, because I had a small number, and so in fact it was very, very easy to do it by hand, more or less. So now if I have, so the 15 to the 8 plus 2, this actually is just 3 times 7. I have to take the second power and the 8th power. 3 times 7 is 21, and I have the answer. This is called the square and multiply algorithm. So if you've never, who has never seen this before? Okay, but it's not so difficult, right? You write the exponent in binary, then you compute all the powers by every time squaring this. 15 squared is 225, mod 37 is 3, squared is 9, squared is mod 37 is 7, okay? And the same thing here, 22 squared, mod 37 is 33, and so on. You can do this exercise. If you want to be sure you understood it, you have to make the calculation yourself again to get some feeling about how it works. But if you do it now here, 25 to the 13, same thing, you get overflow, but you can write 13 as 8 plus 4 plus 1, so you have to take this row, and this row. 22 times 16 times 34. And so the clever thing is that you only work with numbers of at most 4 digits. Right? We start with 2 digits. You only square stuff or multiply stuff. 2 digits and 2 digits is 4 digits, so it always stays small. And then you reduce mod 37, you have 2 digits again. The same thing happens in computers. If you do really Diffie-Hellman, you work with 2,000 bits. So the biggest number you have to represent in your computer is only 4,000 bits. And then you reduce again to 2,000 bits. Of course, you have to have a good library to do this. Or in your ID card, or your bank card, your credit card, there is a special hardware coprocessor that just does this. Because this bank card has an 8 or 16-bit processor. If you would have to do such an RSA, it would take a minute. And also you would need a lot of RAM, extra RAM in the processor, so because they put tiny processors in there, but they put a special hardware processor in to do these calculations. That's what they do. And they're kind of still quite small because the biggest number they have to deal with is 2 times the prime number, which is okay. You never go have a number bigger than p squared, because you can always reduce mod p. And also, if you want to play with it, I think it works with Chrome. There is a professor who made a very nice online calculator where you can do modular calculations. So you first have to enter the modulus. You only have to be careful because he has a keyboard for the digits. But I think the modulus you can enter with your keys of your computer. But for the others, you always have to use his keypad. So it's nice if you have a touchscreen. If not, it's a bit painful. But so if you want to test your calculations, you can actually go there and play with it. This is how you can learn a bit modular arithmetic. So I already mentioned this, that security of Diffie-Hellman is the computational Diffie-Hellman assumption, which means you can't compute alpha to the xy from alpha to the x and alpha to the y. And so Diffie-Hellman is secure because the Diffie-Hellman assumption holds. It's very now, every year, I have at least one student at the exam who believes that by multiplying alpha to the x and alpha to the y, you can get alpha to the xy. Some things in life give me a small heart attack, and this is one of them. Because if you multiply alpha to the x and alpha to the y, you get alpha to the x plus y, and not alpha to the x times y. Okay? So breaking Diffie-Hellman is not so easy. Finding alpha to the xy is very hard, and if you find a way to do this, you can become very rich and very famous. Okay, it's a very good problem to work on. It's a very hard problem. So as I mentioned, discrete log is easier than Diffie-Hellman because if you can solve discrete log, you can solve Diffie-Hellman. So Diffie-Hellman assumption is a stronger assumption because it can be that discrete log is hard, but Diffie-Hellman is easy. But not the other way around. If discrete log is easy, then Diffie-Hellman is always easy as well. Now, in practice, this thing is widely used. I once was looking at products implementing Diffie-Hellman in the 90s. I cannot give you the name of the vendors even now. But you know, it was very easy to break the product because you would just take alpha to the x mod p and replace it by 0. And alpha to the y mod p, replace it also by 0. What happens then? Well, Bob gets 0 raised to the power y. 0 to the y is 0. And Alice takes 0 to the power x mod p, and this is 0. So the key is now 0, and Alice and Bob now share a secret 0, which actually I have chosen. So in fact, you have to check that the values are not 0, or also not 1, because the same work with 1, or minus 1, which in this case is p minus 1. Right? You have to do mod p, so you can add p to minus 1, you get p minus 1. And there is some other tricks you can play. So in practice, as we will see, you have to actually prove that these values are correct. And today we use signatures for this, but in the system I was looking at, I think it was around 1990, so 33 years ago. What they did is they actually picked up the phone and they read the hash value of the Diffie-Hellman values to each other. That's how they were doing this in the financial sector, to make sure that nobody replaced the value by something else. Of course, the cases 0, minus 1, and 1, you can also check by checking the software. But you still may want to ensure that this is the same, that you got the value that was sent, right? So Diffie-Hellman assumes that the right value arrives at the other side. We'll come back to this later. Otherwise, you have a problem. So you assume that the channel is authentic. But even then, you better check for bugs and that you don't get 0, 1, or p minus 1, which is minus 1, as a value. So, in fact, discrete log is hard unless, this is very mathematical, I will not explain it to you, but there is an algorithm. If p minus 1 has many small factors, then discrete log is easy. So if p minus 1 has many small factors, then there is a clever way to compute discrete log. So you have to make sure p minus 1 has no small factors or few, and the best way to do it is to make sure that p minus 1, well, p minus 1 is even, right? Because p is a prime number, a large prime is odd. There is only one even prime number, namely 2. All the other prime numbers are odd. I hope you understand why. Okay, so but p minus 1 is also even, so you can divide it by 2. I mean, the best case, p minus 1 over 2 is actually a prime. And we call this Sophie-Germain primes after the French mathematician, or also safe primes. And mostly in cryptography, you will use those primes. They're a bit harder to find because you first have to find the prime, and then you have to hope that 2p plus 1 is also prime. But again, they're in the standards. In general, we work with safe primes. Don't worry about this. So 1024, we think that NSA factors this for breakfast. So, or computes discrete log for breakfast. 2048, we think is like 4 to 6 years security, maybe 10. 372, this gives you 10 to 20 years of security. The NSA now recommends 3,000 bits or more. And if you're really paranoid, like me, I would use 4,000 bits or so. Right? And there is now even people saying, what about 8,000 bits? But you have to understand something, that if you compute alpha to the x mod p, okay, the number of operations, so more or less what we saw is that you can replace it by square and multiply, right? The number of multiplications, multiplication is quadratic, right? If you have the effort of a multiplication grows with the number of bits of p, we write like this, is squaring. If you make a schoolbook multiplication, you multiply two numbers, you have to actually do all the pairs, right? This is how you multiply stuff. So if this means if you double the number, multiplying them is 4 times harder. Now, exponentiation, the number of bits in x should be the name of number in p, so in fact, exponentiation is cubic. So it grows cubic with the number of bits of p. So it means if you go from 4,000 bits to 8,000 bits, you double. In fact, it becomes 8 times harder, right? So addition is linear, multiplication is quadratic, exponentiation is cubic. So this is why I think not many people will use RSA with 8 or Diffie-Hellman with 8,000 bits, because it becomes really. So today, on a modern machine, it will take you 50 milliseconds or so. If you do the full 8,000 bits, it will probably be in the order of seconds for exchange. Okay, so, but many people already don't like this 2 and 3 and 4,000 bits. So in the 80s, some mathematicians came up with something else. There is some very cool theory called the theory of elliptic curves. And if you remember Fermat's last theorem, you ever heard of this theorem? You don't know about Fermat's last theorem. At least somebody knows. So Fermat looked at the equations of the form x to the n plus y to the n equal to z to the n. And he proved that there were no solutions for n then I think 3. Okay. And then he said, and I found this cool theorem, but the margin of this page is too small to write the proof down. And then in the end, actually, a mathematician, Andrew Weil, in the 90s, locked himself up, or in the 80s already, for 10 years to write the proof. Then he found the proof, then somebody found the bug, another 2 years of lockup. And then he had the proof of this theorem. And it's actually this proof used elliptic curves. So this is how they become more widely known. But in cryptography, you can also work elliptic curves. And the nice thing is that you have much shorter keys. So with a key of 256 bits, you have something like RSA 4,000 bits. And so this is why, more or less, today everybody uses elliptic curves, and Diffie-Hellman with primes is actually no longer be found anywhere. Because you have much shorter keys. The operations are a bit more difficult. I will not teach you how to calculate elliptic curves. It's a bit tricky. It probably takes 2 hours to do the whole thing. It's not so difficult, but it's a bit tricky. It's a very interesting object. But so we believe it's secure with much smaller keys, and this is why everybody now uses elliptic curve. But you should be lucky I'm not going to teach you the math. If you want to learn about it, you can find it on Wikipedia, or there is a book that will teach you, but not today. Okay. So Diffie and Hellman, they couldn't solve the problem of encryption, because with Diffie and Hellman elliptic curve or not, you can only agree on a key. So Alice and Bob now have a key. You can use this key with AES to encrypt a message and say, let's meet tonight at 8. But in fact, the only thing you get out of Diffie-Hellman is a key, not a message. And so Diffie and Hellman, they said, well, we can actually conceptually find a way to do it if we have trapdoor one-way functions. So this is a one-way function. Unless you have extra information, the trapdoor to invert it. Okay? So Diffie and Hellman actually invented the concept, but they invented Diffie-Hellman, but they could not find a construction. So they were from Stanford. I told you with Diffie was first working on AI in MIT, got bored, then learned cryptography, then went to Stanford to work on it. And then actually the guys in MIT, they found the solution to the problem, trapdoor one-way functions, namely Rivest, Shamir, and Edelman. And the idea was very close to what Diffie-Hellman is. So the difference is in RSA, the exponent E is fixed, and very often it's 3 or 2 to the 16 plus 1. That's 65537. That's a Fermat prime, so that's a number of the form 2 to the 4 plus 1. And why people like it? Because if you do square multiply, you have only 2 ones in the exponent, right? To the 16 and 1. So it's actually you square multiply, but you only have to multiply once and square 16 times, so it's a bit more efficient. Of course, 3 is even better. You only need 1 square and 1 multiply. Compute x squared multiplied by x is x to the third. But actually, the real advice, as we will see, is you should use a 32-bit exponent, which nobody does. So everybody uses to the 16 plus 1, but the exponent is fixed. Your modulus is actually variable per user, and it's not a prime number, it's a composite number, it's a product of 2 primes. But so in Diffie-Hellman, the base is 2, and the exponent is variable and secret. Here the base is x, is your plain text, is the secret, and the exponent is always 2 to the 16 plus 1 or 3. So it's fixed. It's a small number for efficiency. And that turns out to be a trapdoor, because finding x from E, M, and Y is a hard problem. It's called the modular root problem. And again, computing roots is easy with Newton-Raphson, but modular roots is hard. So x to the E, computing x from x to the E, your calculator has a function for this. But, or you can use Newton-Raphson, but if they have a modulo there, then it doesn't work anymore. Okay. So here's an example, again, numerical. I took n55, so 5 times 11, the product of 2 primes. I took my exponent 3, like everybody else, lazy. And then I took as secret 17, so 17 to the 3 mod 55. You can compute this with your calculator. You can compute 17 squared mod 55 and then times 17. You'll find 18. So in fact, the third root of 18 is mod 55 is 17. So you can compute modular roots, but in general, this is hard, unless you know the factors of n. If you actually know the factors of n, strange enough, computing modular roots mod p is easy. Okay. But modulo a composite number, computing modular roots is hard, unless you know the factors. So that's what's behind RSA. That's the trapdoor information, is the factors. So of course here it's easy because 55 is easy to factor, but if I take a large number, then it's actually hard. So in public key encryption, so you can send a message, so you apply a trapdoor one-way function. You use a trapdoor one-way function of the recipient of Bob, so the public key of Bob, and you encrypt the message. And then Bob, it's a one-way function, unless you have the trapdoor, and Bob has the trapdoor, the private key, and he can apply the private key function and get the message back. Okay, so we talked in the second or third lecture on chosen plaintext attacks. where the opponent controls the device. Well, in public key, there's no meaning because the public key is known. Anybody can choose any plaintext and compute stuff. In chosen plaintext, you just encrypt a lot of stuff. Right? There is no secrets involved in chosen plaintext. Anybody can do this. It will never teach you anything about the cipher. But what we do see is chosen ciphertext attacks, where the opponent takes a ciphertext and asks you to decrypt it and uses the private key, and that you may actually be able to use it to get information on the private key. So in public key encryption, chosen plaintext is not an attack because anybody can compute as many encrypted plaintext as they want. But chosen ciphertext is a problem because only with the private key can you decrypt stuff. And of course, your public key is public, so it's essential that nobody can find the private key from the public key. So if you go to my homepage, you find my PGP key. It's essential that nobody can factor this number of 4096 bits and find the two factors. If you can do that, then you can read all the confidential email. Right, so that's you have to assume. So this means if your opponent has unlimited power, then you're not secure against them, obviously, because they can just find your private key. So Diffie and Hellman were very close to inventing RSA, but not quite, and I show you what they invented. Well, it was not Diffie and Hellman, it was Pauling and Hellman, somebody else in Stanford. So they invented actually a symmetric key encryption based on modular arithmetic. And why do I show it to you? Not because it's useful, it's a completely useless system, but it's a nice conceptual step towards RSA. So in Pauling-Hellman, you have a large prime number P, and it's kept secret. Okay, so if I put something in red, it means it's secret. Okay. You choose an exponent E, which is, as always, 3, or to the 16 plus 1, whatever. Typically, people choose small exponents. And it should actually have no factors, not with P, but with P minus 1 in common. And for this, you have to study the math part, why it's P minus 1 and not P. And now you compute D as the inverse of E mod P minus 1. Okay, not mod P, but mod P minus 1. And computing an inverse is easy. You can do this with Euclid's algorithm. Again, this is explained in the extra material. You can try this out yourself. It's really not very hard. Okay, but it's important to understand that the inverse is a number. It's an integer. Okay? So here it's, in this case, is, so let me give a simple example. Take mod 7. What is 2 inverse mod 7? That's not 1/2. That's what I sometimes see at exams of people who have not understood model arithmetic. It's 4, because 4 times 2 is 8. This is congruent with 1 mod 7. So it means that the inverse of 2 is 4 mod 7, and the inverse of 4 mod 7 is 2. You see? Because 2 times 4 is 1. So the inverse of 1 over 2 is actually 4 mod 7, and 1 over 4 is 2 mod 7. Does the inverse always exist? No, 0 has no inverse. You can't multiply 0 with something to get 1. Okay? But the good news is if you calculate modulo prime, every number has an inverse. Okay, and so here, in fact, the inverse exists only if E and P minus 1 have no common factors. So if, for example, P minus 1 is even, and if you chose E even, then the inverse would not exist. So there is no number you can multiply with an even number to get 1 mod an even number. Not so hard to show that, because that will never work. But so this is why we have this extra condition. And so to compute this, I just here did it by heart. But there is a method for this. Even if the numbers are hundreds of digits, there is an efficient method to find the inverse. And for those of you who learned in school how to compute the greatest common divisor between two numbers, it's very similar. You start with that, and then you continue a bit more, and you find the inverse. You get it almost for free. And I mean, I think I learned this algorithm when I was 11 or 12, so it can't be hard. Okay. Good. So now how do you encrypt it, Pauling-Hellman? C is m to the power E mod P. So P is secret, E is secret. So in fact, you should not be so smart to pick always 3. In this case, you should have a secret value, a large value. How you decrypt? Well, m is c to the power d mod p. So if e and d are in this relationship, then computing an eth root is the same as computing a dth power. Because the inverse of d is the inverse of e mod p minus 1, not mod p minus 1. Okay? And this you can learn in the number theory lecture, in the small text, and the slides and the exercises, why it's mod p and not mod p minus 1 and not mod p. So this is the Pauling-Hellman system. So if you know p minus 1, you know e, you can compute e inverse and you can decrypt. So this is a secret key algorithm because anybody who can encrypt can decrypt because it's easy to find e from d and d from e. You just can do it based on p. Okay, here's a numerical example. I will skip it, but if you want to understand things better, I recommend that you try these things yourself. So p is 23, e is 13. It's indeed relatively prime with 22. The inverse of d of 13 is minus 5, which is 17. So this uses the algorithm of Euclid. It's an algorithm that's 2,500 years old. It's not very difficult. And so encryption 20 to the 13 is 15, and decryption 15 to the 17 to the d is 23. Mod 23 is indeed 20, so you can check that it actually works. So you have to try this yourself, and then you'll be convinced that it's actually okay. So now what is RSA? RSA is Pauling-Hellman, with this only difference that my modulus is not a prime, but the product of two large primes, p and q. So my n is p times q. And then it turns out that for the rest, the encryption equations and decryption equations are the same. So encryption is m to the e mod n, and e is now public. In Pauling-Hellman, e was secret, but here it's public. And as I told you, it's 3 or 2 to the 16 plus 1. And d is secret, it's red. To the eth root, the exponent for the eth root is kept secret. So now what is the secret? Well, more or less you compute a function of p minus 1 and q minus 1 called the Carmichael function. Okay? And then you compute d as the inverse of e mod this Carmichael function lambda n. But maybe a simpler way to explain is, or a more intuitive way is, in fact, if you calculate mod n, you can calculate mod p and mod q. Okay, like if you have to calculate mod 15, you can calculate mod 3 and mod 5 and then combine the result. Okay, so what you do more or less is you decrypt mod p by computing the inverse of e mod p minus 1. You decrypt mod q by computing the inverse of e mod q minus 1, and then you somehow combine it. It's in fact what we do in practice. In practice, we don't use this. We actually do what I explain here. But so if you know p minus 1 and q minus 1 from Pauling-Hellman, you know you can actually invert. But if you don't know p minus 1 and q minus 1, there is no way we know how to invert this. Because in fact, to find this inverse here, you need to find lambda n. And to find lambda n, you need to find p minus 1 and q minus 1. Okay? That's more or less the problem. So if in Pauling-Hellman, anybody could, once you know p, you can compute the inverse of e. But here, to compute the inverse of e, which is public, you actually have to know lambda n. For lambda n, you have to know p and q. You have to be able to factor. That's the big secret of RSA. So some students at the exam write that d is the inverse of e mod n. Right? And then I get again a small heart attack. Because if that's the case, then anybody can do this. Because everybody knows n. N is the public key. Anybody can put inverses. So in fact, if d is the inverse of e mod n, then RSA is clearly not secure. Because, well, you will find out it's wrong because the value will not work. If you apply such a d, you will not get your plain text back. That's one. But if it would work, it would be really ridiculous because anybody knows n. So anybody can compute then d, and then RSA makes no sense. You can only compute the secret key if you know the factors. Okay. So if factoring is easy, RSA is not secure because you can take my modulus, factor it, and then follow all these steps here and find actually from my public E, you can find D. But if factoring is hard, then we don't know. Maybe there is a way to solve this equation, to solve m from this equation. We call this the eth root problem. And so this is the RSA assumption. The RSA assumption is you can't compute each roots, modular each roots, if you don't know the factors. If you can factor, you can compute modular each roots, right? Because you can just use the steps there. But it could well be that you can compute each roots and you can't factor. So it could be that RSA is insecure while factoring is hard. And in fact, this is a very difficult problem. So whether factoring the modulus and computing each roots are equivalent. And so far, I think since 45 years, there have been 2 papers on this. And one paper says in certain models, the 2 problems may be equivalent. And the other one says in certain problems, in certain settings, the problem may not be equivalent. So we have not made much progress. This is an open problem in science. Whether solving each roots is easier than factoring or not, we don't know. It can be harder, that we know for sure. Okay, so again here a toy example. So P19, Q23, so a toy example, clearly. N is 437, so anybody can multiply them, that's what I make public. Then I have to compute my lambda n, this is least common multiple of 18 and 22. You can compute this as 18 times 22 divided by the greatest common divisor, which is actually, in this case, 2. So this is 198. Exponent E, I chose 13. D is the inverse of 13 mod lambda n mod 198, and not mod n, not mod 437. This is a mistake I see very often, but really that means you haven't understood anything of RSA. Because the real clue is that to compute D from E, the algorithm is easy, but you don't know what the modulus is. Okay? And if this modulus would be known, which is n is known, then it would be easy to break RSA. Okay, so what you make public is the exponent 3 and the modulus 437. What you keep secret is this D, which is, I computed here, it's 61. And here you see a numerical example. So the numbers get slightly bigger already. So you see also here you have to write 13 in binary as 8 plus 4 plus 1. Or here you have to write 61 in binary, and then this is kind of manageable. If not, even this 2 example will already be very painful to do. To use square and multiply. So how do you generate these large primes? There is quite some research on this, and there has been more research on this. But today, even people still use the method proposed called the Rabin-Miller test. So what you do is you generate a very large number. You make sure it's not even, because even numbers tend not to be prime. You make sure it's not divisible by 3, by 5, by 7, so you kind of have a clever way to avoid all multiples of small primes. And then you apply the Rabin-Miller test. And our Miller test may say it's composite. Then you know it's composite. It may also say, I think it's prime, and then you don't know. Okay, then you apply another test with Rabin-Miller, and another one, and after about 10 tests, you're fairly sure it's going to be a prime. But you're not 100% sure there is like an error of 2 to the minus 80 or so. But as engineers, we don't care about this. Mathematicians are shocked by this, but we don't care because with 2 to the minus 80, the Earth will be hit by an asteroid and we'll all be dead tomorrow. So it's okay. 2 to the minus 80 is okay. Okay? So it's good enough for cryptography. And if you want 2 to the minus 100, just do a few more tests of Rabin-Miller and you'll be good. In the meantime, there has been quite some progress to just show you that number theory can move. I think about 15 years ago, a few researchers in India found a test that was very efficient, well, at least theoretically efficient, that has never a mistake. So in the Rabin-Miller test, if you're really, really, really unlucky, it could tell you the result could be of this process could be a composite number that you believe to be prime. With the Indian result, this is a problem that was open for hundreds of years. They actually found a way, a simple way, interesting, to generate primes where you're sure of the answer. And nobody uses it because it's polynomial time with the exponents and the constants are high, so it's kind of like 1,000 times slower than Rabin-Miller. So nobody bothers to use it, right? Nobody wants to wait for hours to get something which you can get in milliseconds, just to be sure. Okay. But the main lesson to be learned from this is that breakthroughs in number theory can happen. Okay, if there would have been a bet amongst mathematicians, I think many would have bet the thousands of dollars that this would not happen. The deterministic polynomial time prime test And then it was done more or less with what mathematics is called elementary math, so most like first-year math, university math. Nothing really deep or so, no like elliptic curve theory or modular form theory, just some simple mathematics to do this. Okay? So if you tell an engineer to generate primes, what he will do is if he does it properly, he will generate a random number, a large number of 1,000 bits, and then make sure it's not even, so you can make the last bit 1, then it's not even, and then you do a few more tests, and then, so you check 3 and so on, and if it's not prime, you add 2 and you test again, and until you find a prime p. In fact, this gives you a bias, because if a prime number is preceded by another prime number 2 steps before, you'll probably never fit it with those methods. But it doesn't matter because there is enough primes. But what some engineers also do, then once they find the prime number, they start incrementing it again by 2 to find the next prime number. Then they have 2 random prime numbers, but they're not so random because the difference between them is small. Okay? Now this sounds like a ridiculous story, but it actually happens in real products. And if the difference between P and Q is small, then you can factor the modulus efficiently. So you have to make sure that the prime numbers are really chosen completely independently, and the difference will be large. But if you choose one close to the other, then you have a problem. So there was once a case of a child kidnapping, and the guy was corresponding with the police using RSA and sending some hints also in encrypted messages. And in fact, he actually chose his prime numbers this way. And one of my friends working for the German Secret Service actually broke his message. And then the people were panicking because the Germans can break RSA. But no, in fact, this guy actually chose his 2 prime numbers so close that it was easy to factor. Okay? Of course, you have to deal with thousands of bits. And so you have to write a library for this or use a library. There is many of those. But it's a bit painful, and many libraries had bugs. So because writing those things is tricky. Or you have to use special hardware, as I said, for chip cards, because it's too expensive. So as I mentioned, people use small public exponents because you gain enormously in efficiency, right? If your exponent only has a few 1 bits, and if you use 2 to the 16 plus 1, you just need 15 squarings and 1 multiplication. So it's very, very fast compared to doing thousands of squarings and 500 of multiplications. So the temptation is too big to use a small exponent. And then, as I already explained, virtually, so as you will also see in the number theory part, for encryption, you don't know P and Q, so you have to calculate mod n. But for decryption, you can compute mod P and mod Q and then combine the result. And why is this so nice? Because exponentiation is cubic. So if I work with half the size, so mod P is half the size of mod n, it's 8 times faster to compute mod P, 8 times faster to compute mod Q, so the sum is 1/8 plus 1/8. It's 4 times faster to calculate mod P and Q and then combine. So in practice, you have a bit of overhead, but it's 3.5 to 4 times faster, plus all your chips need only to deal with the numbers half the size. So everybody uses Chinese remainder theorem to decrypt. To encrypt, you can't because you don't know the factors. But so you actually compute mod P and mod Q, and then you combine the result. Because it's faster and more compact. So before we break, I'll show you some software numbers. You have at least an idea of how expensive this is. So I think DES I showed you, this is like on a quite modern processor. Well, it's 6 years old, but I mean, there is still some progress, but it's not spectacular, right? You still have a factor or two, a factor 2 maybe, but in gigabits. But in cycles per byte, there is not much progress because it's independent of the clock speed, right? Cycles per byte says how many cycles you need on a processor. So I think DES is 30 to 40 cycles per byte, so it's like 80 megabytes per second. So you need about 280 cycles to encrypt with DES. For AES, if you have these Intel instructions, which I mentioned, then you're looking at something like 14 cycles for a block. Okay? So of course, if you don't have these special instructions, then it's more like 60 cycles for a block. Hashing, SHA-2, SHA-3, this is the range 7 to 8 cycles per byte. So we're speaking of 500 to 1,000 cycles because the blocks are quite big. So just calling a hash function costs you 1,000 cycles. Now that's not much because your clock is 3 gigahertz, so 1,000 cycles, This is something like, this is a third of a microsecond, right? It's not very long. Okay. Now, if you do RSA, it takes you 160,000 cycles. Okay, it's a completely different order of magnitude. As for encryption, because you use a small exponent, decryption is like 8 million cycles. Okay, so you see public key is very, very expensive. And of course, if you have a gigahertz processor, it's okay. These 8 million cycles will be a millisecond or a few milliseconds. But you still see that this is very different and very expensive if you have to. You will never use RSA to encrypt all your blocks or so, because it's, as you see, the factor is enormous. And also now you understand why people use small exponents. Because this is how you, of course, gain about a factor 1,000 in number of cycles, because your exponent is much shorter. And you can't use Chinese remainder, so you lose a bit, but then you have a much shorter exponent. Okay, so we'll stop here, and after the break, we'll say a few more things about RSA, and then we'll move on to how you can encrypt. You will also see how El Gamal found out in 1985 how you can actually also encrypt with Diffie-Hellman by adding a small twist, which Diffie and Hellman didn't see in 1975. It took 10 years to find a small twist. We can also encrypt with Diffie-Hellman, actually. That's for after the break.